Hey, welcome back. Working on homework number 3. This is a difficult set of problems and conceptual work. So I was really impressed with a lot of the work that I saw in the homework 3 submissions. I'm just checking our video and audio. And we have video, we have audio, we're good to go. Let's roll. All right, now we're into the part of the course that's called initial value problems. And this is a big part of numerical methods specifically for engineers, where we have these differential equations, we know what forces are involved, we can create what are called the ordinary differential equations, or the equations of motion, of like, this is what I think the world works, like it's some kind of second order differential equation. So then can you use a computer to make an answer that question for you, rather than like solving the exact solutions? Can we just create like these functions that will always give us an answer? And so we did some, in this catch motion, there's, you can use, this is where you'll get all the data for that first problem in order to load in that, the XY data for the projectile motion and save it as a NPZ file. It's another way of like saving your work. So you can like make these variables and save them to a file and then load it up next time you run, rather than like rerunning your work from there. Then revisiting this Euler method, but now doing it for like a general function rather than a hard coding it in every time. Then oscillations, then finally root finding is another big part of these problems, because we don't have an actual like function that we're solving. Like we can't say that x is equal to sine of 3t. It's just x has a whole bunch of numbers, and I can evaluate it at any time t, but I need all the little steps before time t to get there. So finding roots is a big part of that numerical work. So some places where I thought we could use like a little more work. Your polynomial fitting, like I noticed people doing polyfits even in this, where is it? Oh my God, I'm losing my mind here. Even in this question, where I asked you to show that implicit Hume's method has a second order convergence, people were using polyfit to actually find the convergence rate. That's awesome. That is a great way to do that. Of like, here is the decrease in error. Let me do a polyfit and tell you what the slope of that, what the average best fit slope is. Amazing, great work. And I'll show an example of like how to actually get there. But the reason that I'm saying that is that this part seemed great. The only missing piece would be like if you were missing this projectile chords variable, like that value wasn't there, you might have to add a ... / data, because that's where you saved it in this reading, in this part 1 reading. All right, so let's load in this data. So I'll load text of, oh, I should run this first. Load text of ... data falling tennis ball 02. Let's see if that works. All right, I've got T, I'm going to call it like T high resolution. I'm going to follow my own advice. Unlike normally I don't follow my own advice. I call everything T, X, and Y. Here I'm going to actually label it as like high resolution time and high resolution yeah, I like the space there. high resolution Y, so altitude and time. All right, so we have the ball starts somewhere up here, a little over 1.5 meters, so probably dropping out of somebody's hand at eye level, hits the ground, bounces up, and then starts to fall again and bounces. So we have 1, 2, 3 bounces. Roughly each bounce happens at like half a second, 1.5 seconds, and 2 seconds. That's very rough because obviously this is not 1/2, it's somewhere else. But what I wanted to show was when we find this derivative, the one thing that you probably noticed when you were trying to, so this is, let's just turn it into a variable, right? VHR equals that, and then this will be VHR. I gotta use my own variable names. It gives you this long error, and the main thing is that the arrays are different shapes. And this error comes up all the time when you're trying to plot things and trying to make sense of things, and especially when we're using like the same variable names for different problems, you'll definitely end up with different shaped arrays. In this case, it's an easy fix because I can either choose a forward difference or a backward difference derivative. And this is the only difference between a forward difference and a backward difference. If I say 1 to the end, that's a backward difference. The first slope is based on time 1 and time 0. If I say the first slope is based on time 0 and time 1, that's a forward difference. I'll use backward. The data is so dense, it doesn't really matter. But we end up with this kind of sawtooth pattern, and the main thing that I saw people kind of getting hung up on was that they were thinking that impact is an exact time. It's not. Impact takes time, and in this case we're actually looking at the camera is tracking the ball during that the deformation and restitution. So the coefficient of restitution has to do with like before impact happens and after impact. This is more like a physics lesson and like measurement uncertainty kind of problem. But all the data that's in here is all breaking the assumption that this is a ball traveling through the air. Everything inside of here is tracking a ball that's on the ground that has momentum, that is storing it as elastic energy and then reforming, bouncing back and releasing that elastic energy. So long story short, we want this speed and we want that speed. So like 4 and -5 or about 0.8. In practice, it turns out to be like 0.75. So how do I get that? np.max of VHR over np.min of VHR. Here I'm not creating any sectioning of the data at all. I'm just grabbing this max and that min. So this is the speed, and this part's a little weird. This max, because we have positive negative speeds, this is the speed after impact. This is the speed before impact. So add a negative sign. It depends on which physics text. If it's engineering physics, you need the negative sign. If it's physics, probably coefficients of restitution are -1, negative point something. So that's my first coefficient. The next one, I need this max and that min, but I want to ignore this one. So really, I just need everything after t equals 1 second. So what I could do, copy paste, say t hr more than 1. And this is probably going to give me another indexing error, similar to like our plotting, but that's okay. We'll fix it. See, it's telling me like, hey, these dimensions don't match. Look, this is 2499, this is 2500. It's like, it's only one index. Like, come on, man. But we can fix it, right? We'll just start at time 1. Oh, I put the 1 in the wrong spot. A 1 colon. Sorry about that. And look at that. I get 0.7537. Pretty darn close. And it should be the same coefficient of restitution. We'll notice some fluctuations as it's bouncing, but it should be about the same. And I could do the same thing for like after 2 seconds to grab that min and that max. But I wanted to show that because some people ended up with these numbers like around 3/4. Other people were kind of grabbing speeds like in here or over there, like, and it really starts to play with the data. But if you kind of step back and think about it, like when was I actually tracking the position? It's only from here to here. Everything in here I'm not actually tracking. It was on the ground, like it was not moving. Cool. All right. This one, I think I didn't notice many issues coming in here. So I'll skip this one for now and jump into this pendulum swinging, because it's the same kind of process. Like, we're looking at a differential equation, we're trying to integrate it. What is the plot? Like, what is theta as a function of time? In this case, we were looking at height as a function of time. And this one was like, there's no example in the reading of this. And I'll plug in this value first, because this is what I first saw, is that negative g over L times cosine theta. And if it's small angles, then it follows this cosine omega t. But what we'll find out is that it is not small angles. So g over L times np dot cosine of theta, just like that. And you can put it on multiple, I like to put it on multiple lines. So if I make those derivatives, now I need some kind of function to integrate this differential equation. So I have a differential equation, now I need to integrate it. First thing that I always do is just check to see, does it work? So if I give it a position, let's say it's at 0 radians, so it's hanging straight down, and it's not moving, then it will be moving at 0 radians per second, but it will be accelerating at negative 9.81 radians per second squared. That's a little weird, but it's because of this cosine of how this thing was derived. Really, this should be a sine function, because that is a simple pendulum. Well, this one's not simple pendulum because we haven't turned it into a linear differential equation, so it's nonlinear, but that's okay. It is returning arrays full of stuff. So now let's pick an integration method. So I'll go into this part 2, and let's go down. I think this one, the only one here is this Euler step. Is that right? Yeah, Euler step. So we can use Euler step, that's okay. And this will give like a nice example. And I can erase that. If I could actually copy paste correctly. There we go. So now I have an Euler step. And what I'll do is, again, we can, and we're going to say time pendulum. Your time is always an independent variable. I can define time for as long or as little as I want and as many steps as I want. The question for numerical methods is always like, are the time steps small enough? Or the next question is, are they too small? Like, are we using too many time steps to get the same information? Because then we're just wasting computer resources. If it's a one-off thing, if we're just doing the calculation once and we just need a good curve, it doesn't really matter. But if this is something where I'm going to take this model, plug it into some kind of like microcontroller, it becomes much more important to optimize what time steps I'm actually using. So anyway, I can define this any way I want. I like linspace personally, so I'll go from 0 to G over L, root G over L, 2 times NP dot pi, or actually let's go 4. So we get 2 oscillations divided by NP dot square root of G over L, so 9.81 over 1 meter. And let's give it n steps, where n is, we'll say 100, or let's do 101. So we get it. My time step is now based on how many steps I took and how long I want to define this thing. So really I could just say it's T1, but I usually subtract nearest neighbors like this, T1 minus T0. All right, time is set up. I don't need to solve for time. I'm just saying this is the time. And now I can initialize my state, my pendulum state, and then solve for the rest of them. So I'll call it like pend is NP dot zeros. I want it to have T rows, or N rows, and actually since I'm using N, I might as well use it. I want it to be N, the same size as T, but I want it to have 2 columns because I have 2 variables, the theta and theta dot. Pend of my first solution that I already know is my initial value. So it's pi over 6 and 0. Now I can loop through the rest of the values, everything that's not times 0, and solve for what the angle is and what the speed is. For I in range 1, because I'm going to start, rather than start at 0, I'll start at time 1 and go to n, and I'll say pend of I is, and now I don't even need, the way that we kind of defined this whole thing was that that it is that state plus the right hand side times that. So it's going to be this PEND of I minus 1. My right hand side is that pendulum, and dt is the same dt that I just defined right here. And now I'm telling it to take that independent variable time, which I just defined myself, and plot it against the first column of this state variable penned, and that will be all the angles. Oh, it would help if I took my own advice and used my own advice. And I saw some people get this kind of result of like, whoa, it starts to swing, swings really far, and then swings back past where it used to be. This is not, well, there's a couple of things. Here, let's go back. Let's do this like 21 steps. And this was another thing that I saw, that it swings and then starts. And there's two problems here. One is that Euler method is hard. So when we look at the oscillations, pendulums oscillate. So if we're using Euler method, and let's come down. Yeah, anyway, we're looking at the example. So if we're using Euler method, we need really small time steps. So 101 was not enough. We see that energy is not conserved because I'm starting something. So let's fix this problem first. So now it's oscillating more like what I would expect a pendulum, but the amplitude is growing, so I need even more time steps. Now it seems to like start at some value, swing down, and then swing back. So we're starting to fix this, let's say 50,001. It seems like we're fixing this over this 0 to 4 second time span. Now here's the other problem. Angle of 0 was supposed to be an equilibrium angle, but really what we're finding is that angle of negative pi over 2 is the equilibrium angle. Because when I said this differential equation is np dot cosine theta, it should have been sine theta. It was just copy-paste typo. My bad. Things happen. Sorry. But it makes for interesting conversations. So let's change this to sine theta so that the acceleration is proportional to the sine of theta, not the cosine. Because if I say it's a cosine, then really what I'm saying is that theta equals 0 is up at that 90-degree mark, like on the x-axis. But I want to say like y-axis is theta equals 0. And really what I could do is take this whole thing and say add np dot pi over 2, just rotate it, and sure enough, now I'm oscillating through that theta equals 0. It's just this is not pi over 6 anymore. This is pi over 2 plus pi over 6. So let's just go in there and fix it, because Professor Cooper's crazy and he can't keep track of things. So I'll update my function. I didn't change Euler step, but I'll run it anyway. And now I see two periods of oscillation with very much like a cosine kind of wave, because it starts at pi over 6, swings to negative pi over 6, and then back up. Now we're doing well. Then let's do this one. So as we're looking at convergence rates, really for these numerical methods, we care about like convergence on a log plot. Like if time step is 10 times smaller, is the error 10 times smaller, or is it 100 times smaller? So if it's quadratic, if it's a quadratic convergence, the second order convergence, that means when I made the time step 10 times smaller, my answer was 100 times more accurate. That's great. That's very good. Euler's method is a linear, that for time step that's half the size, you get just half the error, rather than a quarter of the error would be squaring it. So let's run through these. and figure out where we get that log-log plot. I'm just running kind of quick convergence. This is the first time that we see like a log-log plot. And then we do it again for Runga-Kutta. And we see here this other time. So one way you can use these readings is kind of like, all right, this code is doing what I want it to. I just need to make a few tweaks to it. So I'll grab this. I'll grab, oh, not that one. That was over here. I'll grab this. And then I don't need that plot, but maybe I'll grab like all of this. And if I try to run it, it'll tell me period is not defined. Like, okay, well, where was that defined? Let me where was period defined? Probably up here, right? Up here. And now RK2 step is not defined. It's like, all right, well, that was that function that returns the next time step solution. So I'll come back down, and I was about to copy it, but I'm like, no, I'll wait for the error to happen. Well, spring mass is not defined. I can grab that too, right? Where did we find that? Where did we define it? Euler Kromer. Spring mass. Here we go. And this one, I'm just going to make. I like to have my functions in a separate. I guess I should have done that for Runga-Kutta, but that's all right. Get error is not defined. Get error is just a subtracting method, but we can copy it over. Get error right here. So now it works for that modified Eulers. I grabbed enough of the code that this thing works, and now I want to do I'm changing the title and Hune's method here. Yeah, I'll add that slash like that. Because what I want to do is in here, I'll just add another one. HEU, like that. And then this one. HEU, HEU. And instead of RK2 step, I need this Hune step. I think it's down here. And I know I'm scrolling around a lot. Hopefully you can watch it in slow-mo and figure out where I'm going. But I grab that Hune step and I'm gonna paste it. I'll make a whole new thing in here, paste it in. I guess, do I need any of that? Because I'm doing that down below. That's what I'm trying to figure out. I don't want to do it twice. So I'm just like taking everything that was numsol and adding that HEU value to it. Let's make that one red. So I forgot to initialize something along here, right? Oh, I forgot to give it this, Hewn step. There we go. And sure enough, modified Euler's and Hewn's method are right on top of each other. Like they're pretty much the same method, just one has implicit integration, the other one's explicit. And then this dash line is showing a slope of 2. So let's take a quick look. This is for almost every implicit method. It will have something that looks like this, where it has a for loop and it has some kind of break in there where it's checking for error. Whenever you ask AI to build one for you, it tries to shoehorn in like an fsolve method into this instead of doing a for loop or a while loop. While loops work the same way as these. I like for loops because I like to plug that max iterations in there. If you do a while loop, then you need 2 if break statements. It doesn't really matter, but because you need to either break if you hit the max iterations or you hit the error tolerance. Again, it doesn't really matter. But this is the main like iterative correction. Like this is what makes or breaks an implicit method. If it doesn't have an iterative correction, then it's an explicit method because it's going to calculate something and move on without checking to see if there's any convergence step. Okay, so that's all I wanted to say for today. I'm sure I'll think of stuff on the next video. I might come back and revisit some of this, especially as we work towards the project. But I wanted to end that here and then yeah, catch up soon. All right.